Muy bien, buenos días para todos en Uruguay, aquí desde Valdivia, Chile. Good afternoon, everyone. Good morning, everyone over there in Uruguay. I will speak in English to introduce our colleague that will do the keynote now, Professor Vournas. I will just read his short bio. I think that if we could really have the bio of Professor Vournas, we would be having a 5 to 10 minutes speech here. So this is a very short overview of what he has done. So Professor Vournas received the Diploma of Electrical and Mechanical Engineering from the National Technical University of Athens, NTUA, in Greece in 1975. The Master of Science in Electrical Engineering from the University of Saskatchewan in Canada in 1978, and the NTUA Doctor of Engineering degree in 1986. He was professor until 2019 and is currently Professor Emeritus in the School of Electrical and Computer Engineering of NTUA. He has published 190 papers in international journals and conferences and has co-authored the book Voltage Stability of Electric Power System, a main document in the area that I'm sure most of the students have read or have in their hands. His research interests are in the area of power system dynamics, stability, and control, and include voltage stability and security analysis, wind generating integration in power systems, novel control applications in the distribution and transmission grid, as well as the effect of deregulation of power systems operation and control. So with this very short bio, I leave you the floor, Costas, for your presentation.
Thank you so much, Lorenzo, for the nice introduction. Hello, everybody from Athens, Greece. We are in the afternoon here, but you are early in the morning, so good morning, everybody. It's unfortunate that we cannot meet in person, but it is lucky that at least we can communicate through the internet. So my talk today is about the voltage stability support that can be offered by wind farms. And I'll give you an example from the system of Greece. So we all know that wind farms are becoming a major part of present day systems. And the question is, apart from giving us carbon-free energy, what else we can get? And this is part of many possible ancillary services. So in this presentation, I will explain how going from synchronous generator to synchronous generator dominated centralized control to converted dominated decentralized control systems, we can have some important functions. And in particular, we can use those distributed resources like the wind farms I will explain in a minute, in order to get stabilizing actions to the main grid. And this stabilizing action can be through the reactive support to the transmission grid. And in doing so, it is important, as you see here, that we should respect the current limits and the voltage limits in the medium voltage feeder where the distributed resources are connected. So it is, as in the case of synchronous generators, we have to respect synchronous generator operation to give ancillary services to the network. The same is true in case that we give these services through the reactive support of wind farms. So in particular, I will explain in a minute that the goal is to use an emergency maximum reactive support scheme. So in case the voltage in the transmission system is dropping, we can have an increase in the maximum power transfer, and this increase in the maximum power transfer will be done through the wind farms that are connected with dedicated medium voltage feeders. Now, what do I mean by dedicated medium voltage feeders is that these feeders, it is customary in the case of Greece, are only connecting the wind farm. There are no loads associated. And this is an important aspect, because if you have loads associated in the same distribution feeder with the distributed generation, then you have an effect of the generator controls, especially voltage controls, on the load consumption. So things will become more complicated if you have in the same feeder both load and generation. The case I'm describing today is simpler in the sense that we only have a wind farm connected in the MV feeder, and in this sense, I call them dedicated MV feeders. As I said, the examples I'm going to give, I'll first give a proof of concept, a very simple system to see what is all about, and then we'll give an example from the Hellenic power system, the power system of Greece, and a weak area that is in the south of Greece, the area of Peloponnese. So conceptually, what I'm showing here is that you have a transmission system, and in this transmission system, you have a number of distributed sources connected anyway. So I'm just giving one, but you can understand that you have many of these sources. Now, when I'm speaking of voltage stability of the transmission system, I'm referring to a particular weak area, a corridor like you see here, where you see this arrow Pmax. And if you have a look at the book that Lorenzo so kindly introduced, the electric power system, voltage stability of electric power systems, you'll see that the definition you give for voltage stability is the inability of the system to transfer the power required to meet the load demand. So you have a maximum power that can be transferred along this corridor, and if you try, because you cannot go past this Pmax, but if the loads try to consume more by increasing their conductance, for instance, then they will cause voltage instability, and instead of getting more power for more demand, they get less power for more demand. This is the structure of voltage instability. So we have a power system that is experiencing a maximum power at some corridor, and the question is how we can increase this maximum loadability Pmax by varying the P and Q, the active and reactive power at the point of common coupling of various distributed sources. This is the structure of the problem. In my case, the distributed sources, as I said, are dedicated feeders connecting wind farms to the transmission system. And we have no control over the P. So the P, I will give cases where it is either constant or variable, but based on a probabilistic phenomenon. So it's stochastic or constant. But we can vary the reactive power through the controls of the feeders. So let me first give you this very simple power system to demonstrate what I am suggesting. So we have a radial transmission system. You see that there is a constant voltage source, E, and at the other end you have a load. The load is a conductance. 1 over G means the resistance is 1 over G. And the power consumed by the load is PL. For simplicity, I assume a unity power factor load. That's why I have only resistance. You see the transmission corridor is reactive. And in the middle of this corridor, I have connected what I call dedicated feeder with a wind farm. So you see here the wind farm. By the way, I apologize that some of the of the writing is in Greek, but I'll explain everything. You don't have to learn Greek to follow this. So this is the wind farm. This is the voltage of the wind farm. This is the feeder, the medium voltage feeder. I have some number of capacitor banks that can control the voltage here, and I have a tap changer on the medium voltage, high voltage transformer connecting the wind farm to the transmission system. This is called load tap changer, or LTC. And as I said, in Greece, it is customary that in each such feeder, the TSO is requesting that the wind producer has installed 3 capacitor banks, 4 megavar each, which are connected according to instructions given by the TSO control center. And of course, the wind farm is not like a synchronous machine. It's connected through a converter, and we assume that it is fully controlled, active and reactive power. The active power is controlled to produce exactly the power given by the wind, PW, and the reactive power is controlled based on 3 systems that we will discuss later. So to get the idea of the maximum voltage, the voltage stability limit, or the maximum active power, we increase linearly the conductance of the load, so the power increases. And as you know, there is one point of the maximum power transfer where by increasing the load conductance, I'll get less power. So indirectly, by this load ramp increase, I get the evolution of the power, and indirectly, I get the maximum power by simulation without doing any computation. Of course, in this system, it's very simple to write down formulae to express the maximum power and whatever else you like. But in the large system I'll be describing later, it is not possible, so we only get indirectly the maximum power through simulation. And this simulation is done using the quasi-steady state approximation. And by quasi-steady state, I mean that all the dynamics that are fast, or so-called short-term dynamics, like generator, the converter I'm describing here, and many others, are at equilibrium. So at each time I change the load, I assume that all the fast dynamics have time to settle to a new equilibrium. So in this sense, this method allows me to get the long-term voltage stability limit without going into the details of modeling maybe a generator here or some other devices. And of course, the tap changer also is acting in discrete time steps. So each time the voltage of the secondary drops, the tap here is adjusted. I'll show this in a minute. So the controls that are available on the wind farm feeder are, first of all, the load tap changer. So you saw the R here is the ratio of on the primary side. And you see if the voltage is above a dead band and I still have steps of taps to change, I increase the tap, because by increasing the tap on the primary, I drop the voltage in the secondary. So if the voltage in the distribution side is above its deadband, then the tap ratio is increased. On the other hand, if the voltage in distribution is below the deadband, then the tap on the primary is decreased. If it is inside the deadband, then the tap remains where it is. Now, you also saw that we have this capacitor bank. This is a variable bank. And as I said, we have usually 3 steps. So in order to coordinate the controls, because the tap changer is controlling the voltage on the secondary, on the distribution side, we decided to make the capacitor banks to switch on or off based not on the distribution voltage, but on the transmission voltage. So for instance, if the voltage in the transmission drops below a minimum value, typically this is something like 95%. So if I have low voltage in the transmission, I switch one capacitor bank. If I have voltage above a certain limit, in this case would be something like above 1 per unit or 1.1 per unit, then I disconnect one capacitor bank. If it is within this min and max, this wide deadband, this is much wider than the deadband of the distribution side, which is plus or minus 1%, something like that. Then if it is inside the deadband, then, or if I have switched on or off all the capacitance, then I do nothing. Now, let me go to the electronic converters that can operate in these simulations in 3 modes concerning the reactive power. As I said, the active power the active power control is such that all power coming from the wind is transmitted through the feeder. So the active power is already committed, but I have an opportunity to control the reactive power. And the 3 methods are the most common if you do not have any requests from the wind farms, is that they will operate at unity power factor, because in this sense they have the less current, thus the less losses on the feeder or the more revenue for the producer. So unity power factor is let's say the standard to start our discussion about reactive support. The second case is when you have constant voltage control on the wind farm end of the feeder. And this is a case which can happen because the wind farm sometimes they want to maintain their voltage within limits. And the third case that I'm showing here is the emergency reactive support, which I'll explain in a minute. So the emergency reactive support, we have the wind farm operating, the wind farm converter operating at constant voltage equal to nominal, 1 per unit voltage. But if the voltage on the primary falls below a limit, and as I said, in the case of the capacitors, if the voltage, transmission voltage is below 95%, you can switch on a capacitor. But if the voltage falls even more, let's say to 90%, then you need emergency support. And the emergency support is given by the wind farm. And if the voltage drops below, let's say 90%, then what happens is that the set point from 1 per unit goes to the maximum permissible value. Usually this is 5% or 8% or 10%. In this case, this simulation I'm using 10%, but this depends on the code on the distribution side, which is the maximum permissible voltage in the distribution feeder. So it switches directly to the maximum voltage and thus provides the maximum reactive support. So the maximum in the title of the method refers in the fact that you go to the limit. Now, it is important to realize that a converter cannot give you any voltage because it cannot give you any amount of current. So you have a current limit, and the current limit, let's say I lim, we usually take it as the nominal apparent power divided by the nominal voltage. So this gives you the nominal current, and we assume that the limit is the nominal. There may be cases where the limit is a little bit above the nominal, but let's take this as a limit right now. So what happens if you are above the limit? Then if you are giving reactive power, then you lower your voltage, okay? Because you are below the limit, but you want also to lower the current. So this algorithm here is such that when you are supporting with reactive power and you have reached the limit, you have to lower the voltage in order to lower your current. The sign here is because you may have a case where your wind farm is absorbing reactive power. So if in this case you absorb too much reactive power and you go to the limit, you have to increase your voltage. But in the case we are considering here, because we are providing reactive support, the only thing we can do is lower the voltage. Now, it is important to realize that this type of behavior in the steady state can be described by a complementarity constraint. And by complementarity constraint, I mean that one of the two inequalities that you see here has to hold as an equality. So either your voltage is on the limit or your current is on the limit, okay? If your voltage is below the limit, then your current must be on the limit. If your current is below limit, then your voltage is equal to this value here, okay? So this is how it looks in the steady state. When you are on maximum reactive support, either your wind farm is giving maximum current or its voltage is equal to the limit and you cannot increase it. Okay, now I was speaking about wind variability. These are just some cases of time series that we have taken from measurements. These are, I'm only showing this to say that these are 1 second samples of wind speed, wind velocity, and we have converted using a model of wind generator of doubly fed asynchronous generator into time series of wind power. And this time series of wind power will give us input to the wind generation. So here is the simulation, one simulation for this simple radial system we were discussing before. I'm giving you the nominal of the wind farm, which is close to 19 MVA, just to show you the effect on the maximum power compared to the capacity of the wind farm. Because if you have large wind farm, you can have larger effect and vice versa. So we'll take several scenarios without the feeder, just a reference scenario, with the switch closed and the variable wind power and unity power factor, just to show the effect of the wind active power on the maximum power transfer. Then we go to constant voltage control and the effect of capacitor banks. As I said, when this voltage, the primary voltage drops, you have more capacitance, up to 3 banks. And finally, the emergency maximum reactive support. So here is the case of unity power factor, because we have the farm. The case without the farm will just show for comparison. Here you see the primary voltage. You see it falls quite a lot. This point C here is where the maximum power is encountered. The maximum power to the load is encountered, okay? F, because this is very low voltage, we have the case with point F, which point F we assume is the voltage static limit. So if the voltage falls below a value here, 85%, we assume that you have a limit of low voltage. So point F marks the low voltage limit, point C marks the maximum power limit. You see how the unity power factor works in the right-hand side. This is the voltage of the distribution side of the transformer. And you see that this is kept constant by the tap changer with ups and downs, because when it goes out, then the tap changes. And you see this is the voltage of the wind farm, and you see it's increasing, varying with the wind, and increasing because it's more required from the feeder to keep the unity power factor. And you see after you reach point B, where your tap changer can no longer control the substation distribution voltage, the voltage drops in both cases. This is the current drawn to show you that in this case you never go to the current limit, so you have no limit on you don't never reach the limit on the converter. And here's the comparison I said. Without the wind farm and with the wind farm with unity power factor, you have a gain, but a very small one of 1 megawatt in the maximum power transfer. Now, what is this curve here? It is the load consumed power, PL, versus the load voltage. So you see point C here is the maximum power, and you see it's at a low voltage. If you do not care to go that far and you say, okay, for low voltage, I want to stop here, then you have your other limit, which is marked by the F, which is the low voltage limit. This is the voltage stability limit. This is the static limit due to low voltage. Okay, so you see with just having the wind blowing, you gain a little bit, but just a little bit. Now let's go to use the capacitor switching and also the unity voltage control, so that the wind farm voltage is unity. And you see when the voltage drops, as I said, below 95%, you have the capacitor switching, so the voltage goes back. You see here the secondary voltage that it can go outside the deadband, but then the tap changer will bring it back. Again, we have the variable wind. That's why you see those changes here. And you see here your maximum power is at point C at a higher voltage. And here is your low voltage limit. And you see in the PV, load power versus load voltage, how you have the increase of almost 6 megawatt. And always the comparison, this delta with the one I showed just previously. So you have another 5.5 megawatts on top of the one that you get from the active power. Now, let me show you what is the emergency reactive support. Point E, as you see, is where the voltage drops below the 90%. This is the primary of the voltage at the primary of the substation. And you see directly, I jump from 1 to 1.1 per unit. And here you see the voltage, first the capacitors, then you have this increase because of the emergency support. You have the limits here. And in this one, you see the voltage on the primary side. With, sorry, the secondary side, where you see the 3 capacitors. And when you have this large jump to 1.1, you see also the LTC is working to reduce the voltage. So if I go again on the PV, load power versus load voltage, you see I increased by another 5 megawatts from what I did using the capacitors and the constant voltage control. And also you see how the point F comes closer to the point C, which is the maximum power versus the low voltage limit. So this is for this simple system, and you can see all the 3 curves together. no wind farm, sorry for the Greek, unity power, constant voltage and capacitors, and on top of this, the EMRS, which starts changing after this point E. So you see that there is quite some room for improvement. And here, what I'm showing is the increase with the EMRS in percent of the available capacity of the wind farm. So you see, this 5 megawatt does not say much as megawatt, but it is about 30% of the nominal of the wind farm. And if I compare, that's for the maximum power, that's the voltage stability limit, VC. If I go with the low voltage limit, VF, I have a similar increase, even higher increase. And here you see the increase with the capacitors as percentage of the nominal megawatt of the capacitor. So you see the capacity is there because about 30% of the wind farm capacity can be given as extra transfer power in the weak corridor. Okay, let me go now to the Hellenic interconnected system. By the way, Hellenic is the Greek word for Greek, so you can say Greek or Hellenic is the same. This system has a long history of voltage instabilities. The worst case was the blackout in the Athens region just before the Olympic Games of 2004. But in the last decade, we have less peak load because of recession first, and also because of too many photovoltaics installed, which in the summer where we used to have the peak load, we also have lots of sun. So the peak goes down because you have more PV generating in the distribution side. However, even though we are much better than what we used to be in 2004, there is still a weak peninsula in the south, in the area of Peloponnese. And this is because we only have high voltage, we don't have extra high voltage. And we have little generation. And so this is a weak part of the system. And in summer of 2010, as I said, 2010 today was the highest summer peak we ever had. We use this as a test case because, as we will see, there was a spotted insecure operating point during the summer. So this is the map of Greece. You see in the north, we have mostly coal-fired lignite stations and also various hydro. The big consumption is in the area of Athens. This is the area of Peloponnese, where you see there are only green lines. There are no 400 kV here. And we have one generating station somewhere here and one smaller one, which is a hydro up there. So this is the weak part if you want to see it on the map. Now, as I said, we spotted one insecure operating point, and this was done using an application that's the online voltage security assessment. And this application was installed in the IPTO, is the Independent Power Transmission Operator. This is the TSO of Greece. So on the control center, we had this application running until recently. The reason they stopped is because they changed the EMS, so they have to have a new installation of this. So right now it's not operating, but it was operating for these 12 years online. As you understand, it was immediately after the blackout that this was installed. And this gives you in the form of the PV curves that I showed before, but in this case, it's not, if you have only one load, it's very easy. If you have many loads, you have to define how you want to show the results. So what we are using is we are using PV curves, which are of a part of a system, in which case we call it the regional PV curve, or national PV curve, which is the total load of the system. So the simulation is again the QSS I was speaking before. And as I said, in June 15, 2010, we had this insecure contingency, which is the loss of one large unit, 300 megawatt thermal unit, while the system load was close to 9,500 megawatts. And in Peloponnese, we had something less than 1,000 megawatts. And the contingency simulated, it never happened, okay? So that's what security means. Security assessment means I want to know what if. So if on this date, June 15, 2010, at about 1-2 p.m., I lost this unit, then I would have had a collapse. This never happened, but in simulation, we know that there was a dangerous contingency. So in simulating this, we simulate the whole system. It's more than 1,000 buses. Some call it large system, some call it small system, but this is what it is. We have more than 100 synchronous generators. I'll show you the effect of some wind farms in the Peloponnese, but these were part of the proposed ancillary service that we're going to show in case these farms were really providing something. Otherwise, they were modeled as passive loads, negative loads in the sense they were producing, but constant P and constant P. So we have the contingency occurring at 100 seconds of simulation time. And then we follow with load increase, but this is not load, this is load demand. Does not mean that the load will cover this demand, because if voltage drops, the load is voltage sensitive. It has a sensitivity of around 1.5%, which means it is something between constant current and constant admittance, but it is changing with voltage. So this ramp here is of load demand, not load consumption. And as I said, we'll do the analysis with the regional and national PV curves. So the area of Peloponnese will show with one representative bus, number is 625, and the national system PV curve will show with this bus number 794. And on top of this simulation, we will show what would be the result of having this EMRS in 14 wind farms that existed at the time in the area of Peloponnese. Did not have any intervention in this event, but we're just checking what if they were able to provide this emergency reactive support. So first go without any support. Again, I apologize for some Greek, but that's why I said 794 is the system PV curve. So you see at point A, we have the unit loss. You see it decreases both the voltage and the consumption, because decrease of voltage creates an increase of consumption. You see that with the load ramp, you can increase the consumption above the initial point, which means the total system looks like stable. It can withstand its demand. But then at point B, we have a second generator loss because of under voltage. This is an under voltage strip, after which things become very, very messy. And at point gamma, you have the loss of one generating unit in Athens area, and then the system collapses. Now, this is the national curve. This here is the PV curve of Peloponnese. You see it's around 0.9, above 0.9 megawatts. I said 900 something, 925 megawatts. You see the loss of the first unit. You see it increases the consumption, but then voltage drops more than the increase of consumption. And you see you cannot reach this point, which means that the system will continue requesting more and getting less until the second unit is lost, and then the third unit is lost, and the system collapses. If you want to see the voltages in terms of time, you see at 100 seconds, you have the loss of the first unit. Then after some time, you have the loss of the second and the loss of the third. Finally, at this point, you have a collapse because the quasi-steady state method cannot converge, which means that the short-term equilibrium point is lost in the system and the system simply collapses. Now, as I said, we will have 11, not 14, 11 wind farms in Peloponnese that are included in the simulation. You see, if you want to keep them as a constant injection, you can stop here. You don't need anything below this point. But if you want to go below this point and you want to change something at the wind farm, you must know how this is connected. And you see, you have various configurations. So this is not one farm. This is a general case, and the 11 wind farms may have only one feeder, in which case S2 is open, or they can have two feeders and then S5 is open, or any combination whatsoever. And you see that by having 3 equivalent generators at most, you can have any of the 11 wind farms in Peloponnese. And as I showed before, it is important that you have all these feeders in as much detail as you can, because the way they can offer reactive support depends on their voltage and also on their maximum current. And you see also the tap changers here and the capacitor banks that are coupled with each transformer. Again, we assume the same type of control, so the capacitors are switched in based on V1. The tap changers are controlling V2 or V5, and the wind farm converters can have any of the controls that I showed before. So if we take a case with constant low wind, which is roughly 10% of nominal. By the way, this was the case when the snapshot was taken, because as I said, we were in the summer peak, and summer peak load means also high temperature, and in order to have high temperature, you do not have wind, because if you had wind, then temperature would drop and you would go below the peak load. So this is the original case, but we also tested with 90% of nominal generation by the wind farms and with a variable wind farm speed and generation that, as I showed before. So you see here the cases where the blue curve is without wind farm representation. The initial case is the same, but there is no change in P and Q injection from the wind farm to the transmission system at the point of common coupling. So you see you have a maximum power in the area of Peloponnese. This is the total load in Peloponnese in terms of simulation time. So you see initially it was above 900, 925. Then you see the maximum without help from the wind farms is below 900. If you go with the black line, which is constant voltage control and capacitor support, you have an increase of 20-something megawatts. You can go close to the initial value, but not quite. And with the emergency reactive support from the 11 farms, you have a gain of about 60 megawatt in maximum power transmission, which means that the system can withstand the initial consumption. So at this point here, they have to stop. There's no need to go any further because the increase of demand is only needed if the load is not served. And you see on the right, the total system load of the Hellenic system. And you see again, the increase that you get from the 11 wind farms in Peloponnese, first with constant voltage control and the support by the capacitors, and then the red curve, which is the emergency reactive support. So you see, you can get from little farms a very large result. And here you can see the substation voltages on the primary, and that's the high voltages of the 11 farms. And here you see the wind farm voltages. So you see that the as I showed before, the switch to maximum reactive support depends on their voltage. So you see one starts first, the others go here. Some stop at some intermediate point, and you see some reach their maximum voltage, and then they have to decrease because they came to their current limits, okay? The one that cannot reach the 1.1 is because it has reached directly the current limit. Now let's see the effect of changing the wind. So this is a case where you have more wind, and the red is the initial one I showed before. The black is with the 90% of nominal of wind active power. And you see now the maximum is increased a lot because you have more wind power, but you see that the reactive support that you give is much less. So in the case of the low wind, you give more than 200 megawatts support. In the case of the high wind, you give less support because you are closer to the maximum. But you see in this case that the more wind, the better in terms of maximum power transfer to the weak area, because this wind is the wind on the weak area. And here are the simulations with a large run of different probabilistic or stochastic wind series. And the important thing to see here is that they all lie between the maximum and the minimum. So in this case, if you take the maximum and the minimum, you have the upper and lower limit of possible support. And this is the average. So I'll just jump to conclusions because we are at the end of the 40 minutes allotted to me. Is this right, Lorenzo?
Yes, so please go ahead for the conclusions.
Okay, so as I showed, the reactive support by wind farms can significantly increase maximum power transfer in weak areas, both in simple systems and more complex real systems. The wind variability in this case is not always the same, but in this case, high wind helps more because it imports less active power, even though it can support less reactive power. The variable or probabilistic stochastic wind gives results that are within the extremes, which is good because you can only do the extremes and know what is the maximum and minimum, but this is not always the case. I repeat, this is specific, case-specific conclusions, not for all cases. Now, the important thing is, if you want to try something similar, that you must always have the detailed as possible modeling of the feeders. And again, I want to stress that this is the case I showed is the simpler one where you have only the wind farm on the feeder. If you have feeder with distributed generation and load, things become more complex and you need more detailed algorithms to increase the maximum power. So this is all from me. I'll be happy to answer questions.
Excellent. Thank you, Costas, for your presentation. Very nice presentation showing also real results and applied to a real system. So we have two questions from the audience that I want to go ahead immediately. So the first question is in terms of voltage dynamic stability, so short term, how the wind pack responds to contingencies have been. Has the system been compromised because of that?
No, well, I'm not sure I follow the question, but let me try to say a few words more about how the wind will respond to contingencies. In this case, the contingency was the loss of one unit. The effect on the wind farm was mostly through the voltage. So it directly felt a lower voltage. Now, depending on the control, if it was just doing voltage control, it would increase the reactive power. So it would somehow help the system. And of course, in the case of the emergency, they are doing something more because they go also to their own limit. So the effect of the contingency on the wind farm is not important because it's not a contingency like a short circuit that can cause disruption of the wind farm. If we had a short circuit, it's a totally different story. I'm not covering it at all in this presentation, but we all know we have this low voltage right through, so they would respond according to the low voltage right through. But now the voltage in the feeder is always is very close to nominal, so there is no such case where the wind farms can be part of the problem. But when the wind farm using the emergency support is trying to help a collapsing system, then it may come to a case where the wind farm itself can become unstable, but this I'll cover in other papers, and I forgot to show the references. So the case of the system stability issues involving distributed sources under adverse network conditions, I refer you to this paper of 2017, and also a recent transactions paper, which is somewhere here, stabilizing controls, where you can see the effect of the collapsing system on the wind farm trying to help the collapsing system. Because if it's not trying to help, it will not feel anything. Sorry for the long answer, but I was trying to cover a lot of things because I was not sure what was exactly the point.
No worries, no worries. That was a perfect answer. So just the last answer I can ask. The other questions that you have posed on the chat, I can I will gather them and send them together to Costas, and then we will see whether we can get some questions by email, Costas.
I can answer offline if I know.
Exactly. Very nice, thank you. So the next question, and the last, is from Agustin Castellano. He's asking, when do you see these being deployed really in the Hellenic interconnected system? Could you see the emergency reactive support combined with wind forecast? Those are two combined questions.
Yeah, okay. The one thing is to convince people to use this, and this requires a change in the codes. So yeah. The codes, remember, they started saying that all distributed generation should be unity power factor. Then they said, no, they have to give some reactive support based on the voltage. Then they also have to have low voltage right through. Now we have to go to the next step, which is to allow for a system where you give something to the wind producer, so that in case of need, like for instance, if the voltage drops, you get this support. The TSO in Greece, they are convinced, and they are trying to move along this direction. So in the next national code, there will be the option of the wind farms to participate in reactive support schemes to the grid, not what exists up to now for low voltage right through, but reactive support to the grid on demand. And the demand can be anything. So if they do this, then they can do what I was showing here, because it's within their capability. And also they can help another problem that I had no time to discuss. When we have high voltages in the transmission system because of light load. And then you need someone to absorb. And the synchronous generators do not want to absorb because they can go unstable, but the wind generators are very willing to absorb because
they could,
provided that they give, some type of contract. So we are on the way. I believe similar things happen in other places in Europe and all over the world. But right now we are trying to overcome the regulatory, let's say, issue first, and then go to some solution. Now, there was a second part of the question on, what was it? The
combining
combined with the wind
EMRs.
forecast. Yeah.
Yes.
Yeah, this is something that has to be discussed. I'm not expert in forecasting, but right now I know that you can forecast wind in short term, I mean, in a few hours with quite good accuracy. So there may be other options there. But what I'm trying to show here is that no matter where is the wind, you may have the same type of contract. And you cannot ask them for everything, but you can ask them for their maximum.
Exactly.
It's the same exactly that exists in the case of low voltage ride through, because they say not only you have to remain in operation, but you have to give 90% of your nominal current as reactive current. So they indirectly specify what you do with the active power. So this type of problem, I think, can exist. And if you have the forecast, then you can have also offers. So you can say, I have so much available for the next hour or something like that. But this is something that we need to discuss further.
For others. Yeah, okay. Well, as I said, time's up. So thank you for the audience for those questions. And thanks to you again, Costas, for your presentation. I hope you have enjoyed
very much welcome.
the presentation over here. Next time, we hope to have you physically close to our colleagues. So thank you very much again. Okay, and I think we just need to disconnect now. So goodbye.
Okay, bye-bye.